Hi everyone, my today's topic is far from equilibrium process. Its definition states that far from equilibrium process occur when a system is driven far from its equilibrium state, resulting in non-linear dynamics pattern formation and emergent behavior. Characteristics: non-linearity system behavior is non-linear and unpredictable. Irreversibility: processes are irreversible with energy dissipation. Complexity: emergent patterns and structure arise. Fluctuations: random fluctuations play a crucial role. Feedback loops: positive and negative feedback loops regulate dynamics. Examples: biological systems that include living organisms, ecosystems, biochemical networks, chemical reaction, oscillating reaction pattern formation, physical systems, turbulent flows, granular media, complex fluids. Social systems include economic markets, population dynamics. Zoological system: Earth's climate, plate tectonics. Living systems are characterized by a high structural order and ordered behavior in space and time. We have already pointed out seeing contradiction between increasing complexity of system in course of its biological development and second law of thermodynamics. This contradiction is easily removed. A living system is an open system whose entropy may increase or decrease usually. One speaks of entropy, nature of life. However, these words can be no way explain specific features of space-time order of an open system, and meaning of anti-entropy concept remain to be obscure. In nature, we encounter two types of orders: static orders and dynamic orders. Let me explain about this. In first case, order is attained under thermodynamic equilibrium conditions when temperature is sufficiently decreased. Say about crystallization of a liquid. Static order arises as a result of phase transition which occurs under equilibrium conditions. This kind of order is not practically found in biology. The dynamic orders of a living system is released not because entropy is dismissed due to a decrease in temperature. The dynamic order of a living system is realized not because the entropy is diminished due to a decrease in temperature. It occurs because there is an outflow of entropy from the one system into the surroundings. The appearance of a space-time structure is in case of two of the nature of a phase of a space-time transition, but a non-equilibrium one this time. Investigation of dynamic order, which are of prime importance in physics and biology, have been started relatively recently. A number of model non-biological systems, in particular chemical systems, are known at present, which are absorbed in a dynamic order. Here we shall cite an example of dynamic order which manifests itself in laser radiation. The atoms of laser are excited by external agency by meaning of optical pumping. Each atom acts like an antenna radiating a light pulse of the order of 3 meter length, the radiation taking only 10-8 seconds. The emission of light by each atom occurs independently of the other atom. However, at a certain level of pumping, there occurs a sharp transition to coherent radiation of very long light plus with a sharply enhanced intensity. The laser itself an open system which is far from equilibrium and in which there arises a dynamic order, the self-organization of coherent emitters. Dynamic order: the appearance of dynamic structures and their ordered behavior in time are possibly only when the system is far from equilibrium. Linear non-equilibrium thermodynamics briefly is valid only in some neighborhood of equilibrium. Its basic propositions are expressed by relations, and the first relation describes the coupling of various kinetic processes due to the reference of the coupling of diagonal coefficients from 0, and the second is a mathematical expression of the Pregonic theorem of minimum entropy production in the stationary state. There is no doubt that the coupled process do occur in upper biological systems. Therefore, the generational phenomenal theory worked out by Onsager and Progenic allows one to account for important biological phenomena. Progenic theorem of minimum entropy production to biological system is more complicated. As we have seen, the entropy production theta is minimum only in those stationary states of biological system which are close to equilibrium. Such systems are described by linear relations. But in physics, the linear dependence of the system's response on the factor responsible for its response is always only the first approximation, which holds for small influence. In our case, the smallness implies a small distance from equilibrium. In order to deal with the biological system and with the dynamic order, it is necessary to be beyond the range of linear thermodynamics. Let us consider far from equilibrium systems. Three situations are encountered. First, the assumption of local equilibrium may be invalid. Second, local equilibrium may be preserved, but the properties of the systems are continuously changed with increasing distance from equilibrium. In such a case, the system retains some of the properties of linear systems. In particular, the theorem of minimum entropy production in the stationary state remains to be valid. And finally, the third case, there appears a dynamic order, new types of organization in the substance,